Okay, hello everyone. Um, Welcome to this stream where I'm going to go through how I finally solved the hardware challenge by q3k. Last time there was some issues with the sound, which I think I sorted out now. So, but yeah, if there's any problem with the sound, please tell me in the chat. So, for those who didn't watch the last time, I'll just go through a short introduction about what we're dealing with here. So, I think it was now 2 weeks ago, q3k posted on Twitter that he had publicly released his challenge called hardflag, which was created for the WCTF finals. Sorry. And encourage people to try it. And as usual, if I see a CTF challenge, I can't resist to try it out. So I said that I would try to do it to a live stream where I solved it without having looked at it before, with the only hints being that it was about RISC-V and Verilog. So I streamed this last week, and it didn't go very well. It was a difficult challenge with a lot of new concepts for me. And I think I tried it for like 2.5 hours without making any significant progress. So I decided to stop the stream at that time, and then I have spent some time during this week or during last week trying to solve the challenge. q3k was kind enough to post some recommended reading materials, which I first went through, and then I tried solving the challenge, and this weekend I managed to solve it. So now I thought I would go through like the process, how I approached this problem, and how I finally managed to solve it. So basically the challenge is we're giving some challenge files. So this is the website where he hosted the challenge, and we're given a zip file or like an archive with some file and an IP address to the server where this device is running. Let's see if we can. Yeah, so the archive contains, I'm just going to collapse some of these directories to get a better overview of it. Let's see, is it possible to get this? Can we? Oh yeah. That's control. Okay, so the archive we get contains, let's see, here is the original contents, and then I've added some files and stuff. So we have one directory called device, one called the VPN client, and one called NICs. And then there's some like a Docker file and a README. So the device consists of a firmware, which is C code containing the firmware running on the device, and then the RTL and these contain Verilog code. So Verilog, for those who are not familiar with it, is a hardware description language. So this is what you would build like CPUs and other circuits with. You like describe them with this language, and then you transform this into a schematic, which then can be used for producing an actual physical circuit. You can also use software tools to like simulate and test and so on. So we're given like a specification for a device together with firmware, and we have this VPN client, which is just a simple Python script setting up a network connection to this this device. The audio is occasionally cutting out. Let's see if I can just... Okay. Looks fine on my end. Please tell me if it happens, if it continues happening. Might be, could be some glitch in some of the cables. Yeah, so this is just a simple script connecting to the VPN client. Okay, so in the last stream, I spent a lot of time just trying to like get the tooling up and getting things to work and trying to run this locally. And then I started reading the firmware code, because that's like where I'm comfortable with, like, you know, regular software C code. And I also started trying to look a little bit at these Verilog files, but yeah, I was I mean, I didn't really get anywhere. It was like a big tangled mess. And that's about how far I got in the stream. I was able to set it up, connect to device, and basically, let's see if we can do that. So yeah, I added some printouts, so this is not in the original version of it. But anyway, this was about as far as I got in the stream. I managed to connect to device, and basically what you can do is, if you read the firmware, it can receive a UDP packet on ports 1337, and you can send a message, and it will try to verify that this is the flag, and if it is the flag, you'll get a congratulations message, and if it's not, you'll get the hack harder message. Okay, so somewhere here there's a vulnerability, and oh yeah, also, like, what I did last time was looking at this firmware code and understanding what it's doing on the software level, and we have this secret config where the flag is, and this leads me to one point I wanted to talk about when you get like a CTF challenge. Like a lot of CTF challenges, or like a lot of these like hacking challenges, they follow like a common format, some kind of setup. Typically, if you're working with like a standard pwnable challenge, the setup is typically that you get an IP and a port, and if you connect to it, the program you're trying to pwn is connected to that socket, and the goal is to get code execution and read the flag from like a flag.txt in the same directory or something. That's like a standard setup. Another standard setup for like a reverse engineering is a crack me challenge, where you get some program which you can give some input, and it would tell you if it's the right input or not. Basically, like you should give it a flag, and it will say if it's the flag or not. So that's like a standard setup. But in this case, I mean, it's not like super. It wasn't obvious to start with. Like, okay, we have a device running some kind of firmware. So, is the goal to get like code execution, or does it only is it enough to like leak memory or whatnot? So, like, one first step is to just try to figure out like what's the end goal here. Like, where are we going? So, by looking around here in the firmware code, we see that there is like a flag in memory. So the end goal will be to leak this flag from the production server. And then what we typically would do is to try to do this locally first, and then when we have a working method, we will run it against the like real production or target server. But then, of course, there might be a lot of steps between like where where am I now, and this end goal. But it's at least that's something to know. Like, okay, this is where the flag is, and it could be, for example, if you're looking at a web challenge or something, it might be like, is the flag in the source code, or is it in a database, or like what are we trying to do? But and also basically looking at this firmware, we could find out basically what it does. It receives packets over the Ethernet, and then it can handle ICMP packets, which is like it will reply to a ping. It can reply to an ARP request, and it can process this UDP packet. And that's about as far as I got on the stream, I think. Some other things. But so after the stream, I looked at this recommended reading. So we're given a nice little list here. And I will start. So my background when it comes to like hardware and electronics is that like I'm interested in the topic. I'm a hobbyist, like on electronics on a fairly basic level. Like I can assemble some basic circuits, and I could probably design some very basic circuits as well. And I studied physics at university, so I have like some basic understanding of a lot of the concepts. I once took a really interesting online course. I don't know if it's called NAND to Tetris. Yeah, it's basically a course where you build your own CPU from like starting from a simple NAND gate. You build your all the way up to a working, like a very working basic CPU, which you can run code on. It's very good course. I can recommend it to like understand some basic things about how computers work. But that's basically my background. So when looking at this recommended reading, you have a like basic digital logic and some course in that from Imperial College of London, and I felt that okay, that much I think I know. So the other things were really interesting. So one thing is some lecture slides about state machines in Verilog, and yeah, it's some slides about how to represent like about finite state machines, which is also a topic I'm familiar with. So I didn't spend that much time on this. It's basically a description of like what is a finite state machines, different types of state machines, and how you can represent them in first, like conceptually, how you would represent them, and then some concrete examples how you could implement this in Verilog. And my experience with Verilog is pretty much non-existent. So as I said, I had taken this NAND to Tetris course in which they use their own like HDL, like hardware description language, but like it's like a toy HDL, which is very it has some like the basic features you would need for that course, but it's not like a real HDL used for actual production stuff, which Verilog is. So there's a lot of like syntax and stuff that I mean I could some of it I can guess, but I'm not that familiar with it. So it was also interesting at this point just to see examples of Verilog to kind of understand the syntax. Yeah, so I mean I read through these slides, and oh yeah, also gained another like bit of insight from reading this is that it might be good to have some like when working with this, it might be good to have some kind of like wave like analysis tool where you can look at the actual signals, and one such tool is GTK. That was very difficult to say. GTK Wave, which looks pretty much like this, but it's a different program. So I used that a lot during this process. But I mean, I didn't spend that much time on this, and yeah, it's some basic stuff, good to know. But the rest of this list is what really, or like these 3 topics is what really, what I really spent some time to try to understand. So if we look at this Verilog code again, we have this Pico RV32, which, and I did this on the stream. This is an implementation. It's an implementation of a RISC-V processor in Verilog. And what I did on the last stream was I actually, because I assumed that they didn't build a whole processor for just this challenge. So, and also here it says it's built by Clifford Wolf. So I looked it up in his repository and compared it, and it was they were identical. So I assume that this is simply a working RISC-V processor without any bugs, at least any bugs that affect this challenge. So I kind of assumed that I could trust this part. And then you have these components which are called AXI4, and then some different AXI4 Ethernet, interconnect, memory, UART, and then things called FIFO and TOP. And so this AXI4 is something I've never heard about it before. And also, if you looked at in some of these files, so typically in a Verilog file, you have modules, which is like chips or part of a chip, and a module has inputs and outputs. And in the beginning of your module, you specify your inputs and outputs and how big they should be. And a lot of them here were named like AXI. So like the majority of them are named AXI. So this is presumably then some kind of communications protocol or some kind of communication thing, but I have no idea what it is. So one of these recommended readers is the AXI4 reference, which is an 82-page technical document with a lot of stuff that I didn't know about. And here I really didn't feel like reading all of this because I thought I just need like the very basic gist of it. I mean, I'm not going to implement this, or I don't need to know all the nitty-gritty details about this. I just need to know enough to understand how to work with it. So what I did was, when I looked at this, these different components, let's pick up like the Ethernet and a memory, like yeah, all of these AXI inputs and outputs, the names seem to be grouped together in different groups. So I have all of these like AW, and some of them are called AR, and then some of them are just called like R or W, and then there is B as well. So I kind of guessed that this was, as they're written here in the memory, that's some kind of like natural grouping of this, but I still don't know really what this is. So before I went through this like AXI reference, I looked at this FIFO document. So this is some like lecture slides or something from Berkeley, from electronic engineering course. And this is basically a specification for like a simple way of 2 modules communicating with each other. So in this setup, you have two modules and three signals, and this is like a one-way communication. So you have the data line and you have a valid and ready line. So when the source is ready to send data, it will put some data on the data line and it will toggle the valid line on to say like, hey, here's some new data that you might want, but only if the receiving module has this ready flag saying like I'm ready to receive. So the sync says like I'm ready to receive, so the source says okay, here is some data, and you will toggle the valid flag for one clock cycle to indicate like this is new data, and this way we can transfer chunks of data. So every clock cycle we can put some new data in on the data line, and as long as this ready thing is still up to receive. And this is interesting because you see the names here: valid, data, and ready, which corresponds fairly well. Here we have valid, or you see all of these have like valid, ready, and then like this has adder and this is data, and so there's like some difference. But so here I'm starting to like realize that this is somehow consists of five such FIFOs in a group together, and this is when I looked at the this AXI reference. So as I said, I didn't want to read the whole thing. So basically, I was just looking for some kind of like table or something which would explain all these different things to me. So I basically just took one of these names like W ready, and I searched in this manual, and it turns out that at the end there's an appendix which is called AXI adoption summary. Here they have some tables, AXI4 and AXI Lite signals. So that seems good. But here there are like a lot of different signals, and we don't have that many signals in our thing. So what's the deal? But if you look here in this other column, they have AXI4 Lite, and a lot of these are like signal not present. So maybe this is actually AXI4 Lite, and that would explain it. So if we look in the table, we will find this like W ready, for example, and which is a part of this. So if we look again what we had like valid, ready, data, and stir B. So and that, so you have the data, the stir B, and the last and user not present, and then valid and ready is there. So this seems to correspond fairly well to this table. And what I then also managed to do, I think I was like, yeah, exactly here. So I just also read a little bit of the introduction in like what is AXI4. And here they have a really nice paragraph. How AXI works. So both AXI4 and AXI4 Lite interfaces consist of 5 different channels, and that corresponds very well to what we've seen so far, like 5 different groups of these FIFOs. So you have read address channel, write address channel, read data, and write response. So this is like a full duplex interface. You can read and write over this at the same time. So how it works is that when writing data, for example, you will put the address of where you want to write, you will put in the write address channel, and then the actual data you want to write, you put in the write data channel. And same thing if you want to read an address, you put the address in the read address channel, and you will get the data from the read data channel. And the write response is like could be I guess like an acknowledgement or something that you've written that it works, that it worked. And so that's good. So that means that basically we can like treat this whole thing as just like, okay, this is just a generic read-write interface which supports reading and writing from different addresses. So yeah, that's interesting. Which means that like mentally, this is, or like conceptually, this is no longer like a module with like 20 different inputs and outputs, but this is more like one module with like a clock input and a read-write interface, and then just some, let's say, like tests passed. So just some testing interface. I guess we don't really have to care about that. Okay, so that's a very good example of like we have this seemingly complicated thing, but then when we understand it, or at least understand it better, we can like abstract it into just one simple concept. And this is very common. For example, when reverse engineering something, you might find some mysterious function. You don't know really what it does. So you analyze it and you find out like, okay, this is maybe like a decryption routine. So then you can name that thing like, okay, this is like decrypt data, and then you can just treat that from that point on. You can treat it as a black box thing. Just this decrypts some data, and it's important that like when you're doing this is, I mean, unless you read everything down to the byte, and not even then, you're like 100% sure that you're correct, but you kind of like make an assumption, and then we create this like abstraction based on this assumption, and then we continue going to get some kind of speed on this. So, I mean, at this stage, I didn't check that like all of these were correctly wired into this thing. I mean, I don't even know what that would look like or what it would not look like, but right now we can just assume that this is like a read-write interface to this memory module. And this leads me to like a general idea I have when like reverse engineering or understanding like big complex things like that. And before the stream I thought about a little bit like how what is like a good analogy for this, and I came up with a really good idea. So I think like many of you might have like, you know, one of these boxes where you put all like your like extra cables and stuff in it, which you put in your you know, somewhere in your storage, and all the extra cables goes there, and then one day you pull this horrible mess out and it's all like really tangled up, and you want to try to like make sense of this, like detangle this. You have this whole big mess of cables, and at first glance it just looks like, you know, like one big knot, which is like everything is interconnected, and a very big problem to tackle. And then you start recognizing maybe like, okay, I see like this is part of like an Ethernet cable, so there should be like two ends of it, and it's blue, like, so there should be like two blue ends of an Ethernet cable somewhere in this mess. And you maybe start looking a little bit, and you see something else you recognize, and then suddenly you see that, okay, this is not actually like one big tangled mess, it's more like two big tangled mess, so I can like separate them into two parts, and then you like continue onwards like that, trying to, you know, you go to specific things and try to understand some details, which, and then you like back off and look at the big picture again, and you kind of move back and forth between these two modes. And like one key to being like efficient is to kind of like feel like when you have enough of understanding of the details to utilize that to like better understand the bigger picture. So yes, we have, as I said, we have these. So now we kind of know what AXI4 is, And if we look at these components, we have an Ethernet device, a memory device, a UART, which is like communications, like external communications thing, for example, and the interconnect. So if we look at the interconnect, because that sounds like something that would connect the other things together, reasonable. So some kind of hub. So the interconnect defines, like we have one AXI interface here, which is called like slave 0 CPU, and then it has another one which is called Ethernet DMA, another one master IRAM, master UART, master Ethernet. So it's basically a module defining. So at first, if we would have looked at this without understanding what AXI is, we see like all of these lines. That's like 100 lines of inputs and outputs, or at least like 80. But now, when we understand that this is just like a generic like read-write protocol, we actually see that this is like 1, 2, 3, 4, 5 connectors. So it's like a hub with 5 ports, basically, and some comments here where they're going to be wired. Okay, but where is the actual connection happening? Because here we see no reference. So if we look at this, take this module, the AXI for Ethernet, and search for it in the interconnect, there are no results. So the actual connecting these things together is not here. But if we do search for it in like all of these files, we find it in the top module, and that, like in hindsight, makes a lot of sense. Like the top module would be like the entry point of your design. So that might, I mean, I felt a little bit stupid. Like, why did I wait so long before I actually looked in this top module? But hey, mistakes were made. So here we see a lot of stuff, but we see specifically these modules. So this is like a Verilog. In this Verilog code, like we have one module called the top module, and in this we can like instantiate other modules. So here we instantiate this memory module, and then we connect the inputs and outputs to these wires in this top module that we have defined. And the same thing with the UART, the Ethernet, and here we have the CPU, which we also connect to the this interconnect thing. Exactly. So we connect the CPU to the memory, and that's interesting. So now we could pretty much draw like a small sketch, and actually so I actually did try to, like when I was doing this, and this is something I do sometimes as well. I mean, a lot of stuff I do like on computer digitally, but sometimes it's just more nice to. So I don't know if I can like, will this come out? Yeah, I think it's viewable. So I kind of like draw a small picture of how these modules were connected together. Just to get some kind of more like write things down that I know to get some kind of understanding. Okay, so now we have some kind of like understanding what all of these pieces are doing, but we here looking for some kind of bug. Like there's something wrong somewhere, like either in one of these Verilog files or in the firmware or somewhere. And we still have no idea where this is. So we're still like at kind of like a reconnaissance stage, or like reverse engineering stage, where we're trying to understand what we're dealing with. And we need to, like, this is a lot of stuff. Like, for example, this processor thing is like a couple of thousand lines of Verilog code. And I mean, I said I assume that this processor is fine, but still, like, looking at all of these others, they're like a couple of hundred lines each of something that I'm not like super familiar with. So how do we like reduce the scope? How do we rule out some things here? And this is where we get into these SBY files and the formal verification stuff. So back to the recommended reading. There was like, what's up with all those SBY files and formal verification? So this is a link to some presentation slides by Clifford Wolf on formal verification with Symbiosis and Yosys SMT-BMC. And first I started just like reading the slides, but then I realized that maybe the actual presentation is somewhere to be found. So I just like Googled this title, and I ended up on like the YouTube channel of the CCC conference where he gave this presentation. Eventually, I also found on Clifford's own website, he has links to a lot of research, but one of them is this formal verification with Symbiosis and Yosys SMT-BMC. And here you have, this is like an updated version of the same slides linked here. So you have the slides, and you also have a video recording of this presentation at a university. So I just went ahead and listened to the whole presentation. It's really interesting. You should have a look at it. But the key takeaways from it is that we can use some of these slides as some support here. So a circuit can be in a number of different states, and they are typically, like, for any reasonable circuit, that's typically like a lot of states. And some of these states are like initial states, and typically it's maybe just like one initial state. And you have some bad states where you're in a configuration where you shouldn't be. And the presentation describes how we can do a formal verification of this, like proving that from the initial states we cannot reach any bad state, and that means that the design of the circuit is correct. And some of the challenges here is to actually define like what is the actually correct behavior, and then you can use this tool, Yosys SMT-BMC, which uses SMT solvers on this like state graph to prove that the design is correct. And these SBY files, they are kind of like a configuration file project definition of for Yosys to do this formal verification. So you can easily install like Yosys and these other tools. Let's see if I scroll down to the right place here. So you can install like Yosys and this Symbiosis, which is like a helper script to make it more simple, and then you can use this to like run one of these SBY files with Symbiosis to do this verification. So the way it works is that if we take this interconnect file, for example, the Verilog file, let's check it. In this Verilog file, there's one portion of it which has this like if def formal, and it's a block. It's basically the rest of the file. So this part of the code is just used for the verification. So in this you put different assumptions and assertions that you want to test. So basically for example, this block here, we're saying that if we just reset the circuit, then all of these things should be 0. And then you give this to the prover to see if it can find a counterexample. And if it can't find a counterexample, then we have proven that this property holds, and this is correct. So if we look at the files we have, we see that we have 1, 2, 3, 4, 5, 6 different Verilog files, but just 2 different SBY files. So I just made a wild assumption that the components which has an SBY file, they are correct because they have some kind of test code in them, and like you can run this with the Symbiosis tool and it will say that it passes all the tests. Now that is admittedly a bit of a leap of faith, because I have no idea that these test cases are reasonable for this kind of component. I have like, does this test all the properties which you would expect from this component, or have we missed something? But I need to start somewhere. So the initial assumption was that the interconnect module and the FIFO module, they are fine. There was also, so together with the challenge, there were some hints in a hints file, and I actually used these hints, and the hints basically said that there is a bug in the Ethernet device, and specifically with the Ethernet DMA access. Now, I wasn't really sure if this meant that the bug is actually in the Ethernet module or like in the memory module. Like in theory, it could be that like the addresses which the Ethernet device tries to write to is somehow interpreted incorrectly or something. So we're like, the memory module is not completely off the hook yet. And the top module, if you look at it, it's basically just like connecting all of these devices together. There isn't really any like logic or anything of its own in this part. It's just like creating all these connections between the different devices. So I left that out for the moment. So and like the UART module is just for like printing things out to the terminal here. So that also felt like it just reads data. So that didn't really feel very interesting at the moment either. So basically we're left like with the Ethernet and the memory module, where like the Ethernet module is the prime suspect, because I mean, first of all, because it's typically a more interesting device, and also because it was given in the hint. Okay, so where does that leave us? So we have this Ethernet device in which we suspect that there is a bug with how it accesses the memory when it's doing this DMA. So I started first basically looking more into like you see, there's a lot of logic in this code. Like it depending on different states of different registers, it writes different values to other registers and so on. So this was still very like I didn't yet really start digging into one of these like functions or blocks, because I mean I had no idea what I was really looking for. But I started with like trying to understand exactly how this relationship with the CPU, the Ethernet, and the memory device. So notice that the Ethernet device has 2 of these AXI ports, one of them is connected to the CPU and one of them is connected to the memory. And if we look at the firmware in the startup, in the main function here, we see that we have these registers which are called like receive ring start, receive ring end, receive write pointer, receive read pointer, and then this state which enables features on the Ethernet controller. So it looks like we're giving the Ethernet device a pointer to somewhere in memory and saying like, here is a ring buffer which you can use. And at one point I actually looked up all the places where the firmware access these control registers of the Ethernet controller. So apart from this, setting up this ring buffer with the read and write pointer, we also have, when you send a packet, we basically give the Ethernet controller, we write to this register transmit packet start, so we give it a pointer to where in memory is the packet we want to send located. So this seems to be like the interface between the CPU and the memory and the Ethernet. Like the protocol is that when it looks like the protocol is like when the Ethernet module receives a packet, it will write it to memory within this ring buffer, and then it will if we look at the code, it will trigger this interrupt handler, in which the packet is then actually like read and processed. And when we want to send a packet, we just give it a pointer to somewhere in the memory where this packet is located. Okay, so that gives us at least two possibilities of how this could go wrong. So, and this leads us to like another point when doing this kind of challenges. So, as I stated in the beginning, we have this end goal of leaking this flag, and we will reach that end goal through like one or multiple intermediate steps. So like what is the path we're going to take to actually leaking the flag? And here we can see two possible paths. So if we, for example, would get this write pointer corrupted somehow, then maybe we could write memory to overwrite arbitrary memory somewhere in the code, and that's a typically like one primitive you're looking for when like exploiting something, like an arbitrary write. That's usually useful. We don't really know exactly for what yet, because like we want to extract memory, not like, but this could be a stepping stone to that. Or maybe if we could overwrite this read pointer when we're sending packets, so it gets confused and just sends data from somewhere else in memory, then we would possibly directly leak the specified, like the target memory. So that could be another strategy. And we still don't know like if we're gonna need like both of these, if we're gonna, or just one of them, or maybe it's something completely different. But that's just like something to keep in mind. Like if we could corrupt the write pointer, we could write outside this ring buffer, and if we could in somehow some way corrupt this the read pointer when sending packet, we could leak memory. So that's a good mental note. I'm gonna check more here in some of my notes what I did. So what I did was I thought that I would do some of this, try out some like formal verification of this like Ethernet module to try to set up, I mean, just to prove something, or you know, just try it out. So I started experimenting with this like Yosus and Yosus SMT BMC, and first I just did some like toy experiment. Let's see if we can now go into, so everything up until now I've been browsing within just these like this untouched archive, but now we will look at things where I have like modified these files a little bit. So let's see if I actually kept some of that code. Yeah, I started playing around basically with this and things like that I would assume that on the first cycle we reset the device, and one idea at one point I had was that if for example okay, so let's back up a little bit. This Ethernet device defines an MTU, what's called like the maximum transmission unit, I think that's what it's called, which is like the number of bits per block it can process. This is, if you have something that's bigger than this, you will get fragmentation and then other more advanced network topics. But anyway, the way the Ethernet controller works is that you have this part, which is like the actual like the Ethernet connection, the Ethernet port. So you can have data going in and out. So then we know that if this like these are also these FIFOs. You have data valid ready, data valid ready. So we know that this data valid means that if this signal is high, then we have data incoming. So let's look where that is used. So here basically we have a couple of conditions, but essentially if this incoming thing is valid, we will set this to high, and as long as some other we have these other two flags like interested and overflow. Interested is pretty fun because this essentially defines the MAC address of the device. So this interested checks that if we have enabled the broadcasts and the first part of the Ethernet frame is like all set, then we are interested. Or if we have enabled receiving packets and the first part is this, and this matches in the firmware. So let's go into the firmware where we do the here. So this is the these constants are used when initializing the Ethernet structures, and it's the MAC address of the device. So we can see it here reflected. Here it is in software, and here. Oh yeah, I shouldn't mix these up. I should just use the ones from which I have commented and stuff. So here the MAC address is in hardware basically. So if it's one of those cases that either it's a broadcast or it's a targeted packet, we are interested. And if we are interested, we start receiving data, and we set this right pointer to some, like this is all like latched, and this is like something I'm not like super confident in, but basically this is like a delayed, so this will then happen like one clock cycle later. Some hardware person might correct me or something in the chat, but yeah. So okay, we we assign this data to this like receive thing, and then in this block here we have this receive selector, which will like shift the data down and put it in this AXI write signal. So this is how the received data is transferred from the Ethernet device over the AXI protocol into the memory. So then, and at some point I have this idea about so what happens if we try to like send, like what happens if this thing goes too high, then we will just shift this down to, I guess that would just be 0. But then I started thinking about, okay, but what about sending the data? So this is the incoming data that we receive. So seems like the only way we could make this be like messed up is if we can control so it seems like we can't really control like the actual data written in any meaningful way, but maybe we can control the address that we are writing to. So if we look at this like address on the AXI protocol, we see that it is only used in this block. So depending on, so this is like a wraparound of the ring buffer where we're gonna write. So yeah, so q3k pointed out like these less than or equal to sign is like this is one situation where these ligatures are not that useful, but this is not a comparison. It's like an asynchronous assignment. So compared to like in a typical programming language, you would do like something like this, which means that first we assign to A, and then we assign like this value plus 3 to B. But and you can do that in Verilog as well. But what you typically do is you have these blocks of asynchronous assignments. So all of these are happening at the same time. So that's good to know. Anyway, so I mean I couldn't see anything obviously bad with the receiving of the data here at this time. Just like searching where the data comes, but let's look at the other way. So when we send data, we will put it on this this signal. So where is that set? It's just the contents of this transmit latch. So where is that used? It's basically used here, and this is like a concatenation. So we read some data from the AXI, and then we like shift this, like part of this is connected to this shift thing and it's shifted back. So we shift in one block at a time into this buffer, and then we send it. So again, where is this like this data is read from somewhere, so where is that address used? Here is the read address of the DMA thing, and it says like we're gonna start at this packet start pointer, which is given from the firmware, and we're gonna add the chunks counter. So here was another idea, like maybe we could get this if this chunks counter goes to high, maybe we can like read out of bounds. And yeah, and q3k points out that it's called a non-blocking assignment, not a synchronous assignment. And I'm just gonna take his word for that. I have no idea what's the difference in this case. Anyway, if we could get this to go too high, then maybe we could do something. So let's see what this is, where this is used. It's, I mean, here it's reset and it's incremented, and it's incremented as long as we have chunks left, and chunks left is set to chunks at the start of the transmission, and chunks is a constant, which is the MTU divided by 32. So here we have a good property which we can test, because the chunks, this means that the chunks counter should, in a correct circuit, since we will set the chunks left counter to chunks, and then we will like count the chunks left down, and we will count the chunks counter up. So that means that the chunks counter should never go above this chunks constant. So this is where I was going with all of this. Did I? Oh yeah. Sorry, opened the wrong one. So I created this assertion here. Like in each clock cycle, we assert that the chunks counter is less than or equal to the chunks constant. So that's a good test, because if we manage to break this assertion, that means it's possible to like read out of bounds in a like a non-intended way. So I set up this this SPY file, and where we read this the module, and what we're gonna do is there are like multiple modes you can run this in, and basically the BMC mode is just starting at the initial state and then going forward for a certain number of steps, see if we can reach an incorrect state. And I tried different values in here, and I mean, of course, the higher you set this, the slower the whole thing will be. And this, like in most examples, it was like 20 or 50 or 100, but I just set it a bit higher just to be sure. So I thought that like maybe we could somehow in 150 steps we can manage to break this. So I ran this, but it passed the test. So there, like according to Yosis, there is no way of invalidating this assertion within 150 steps. Okay, so that was like a bit disappointing, and I've tried a number of different things here. One general strategy was like, okay, I want to first set the Ethernet controller in a specific state, because this was like one of the problems I had while testing, because except for a very short period in the beginning, like all of these things will have some specific value. So I wanted to kind of like emulate that, and here I used a kind of like a neat trick, because I thought it was like bothersome to manually type out like this, like all these signals to set these things to a specific value. So basically what I did was that I created some assertions where, and they were on the form like, assume that this value is not equal to like a specific hex value. something like this. What I did here is I actually took I ran the, let's see if this output, yeah, okay, in the firmware. Yeah, so this is maybe something I should talk about. So, okay, hold this thought for a second. I'm just gonna do a small detour. So, if we are building a real physical circuit, we would take this Verilog code and we would run it through something, a tool, and then it would produce like a schematic, which could then be used to construct a real physical device. But when we're simulating this, we kind of want we're not building a physical circuit. We just want to like build this, like a model of this, and simulate it. And one way to do that is with a tool called Verilator, and it allows you to like generate like a C++ model of this circuit, and then you can interface with this circuit with your like C++ code. So what I did, and I will get to this later, but to like try some of my assumptions and to like understand some of the states and stuff going on in the processor, I modified this Verilator code to like print out different registers and parts of memory in each loop. But if we just like comment these prints out for a second and we run this thing again, yes, and then if we look at the firmware, we see that it had this defined state, like if ETH debug, and it would print out like the addresses of these registers and some other things. So that's interesting. So I compile it with this flag, and then when you connect to it with this VPN client, yeah, there, and send the packet, it would print out these the addresses of these buffers. So I actually, and these were the same all the time, which makes sense because there's no like memory randomization or anything. So I actually used these values for my test cases. So I set up things like this, like assume that this control register cannot have this value, and we of course know this is false because we just ran the program, it had its value. But the point of this is that instead of like manually creating these signals in hardware which will set the correct values, I will just let the prover construct them for me. So basically I said that I did like a combination, like assume like this can't be this or this, and like for all these registers, and then I ran it, and when you run and then of course it will fail the test because the solver will find a way to make all of these statements, this statement false. Like it will find a way to make the value of this register this value, and what it will do is it will construct like a model of this, which is useful. It will do something like this. It will say that in the first cycle you set all the inputs to this, and then in the second cycle you set all the inputs to that, and so on. So then I could just copy those values over to a new test hey, where did into a new Verilog file. So this was a way of like using this formal verification tool to kind of like create these signals to creating this initial state. So here I kind of like created another module which contains the Ethernet module, and the way this works is that on the first like X cycles I manually control the inputs in the same way. I have like in this cycle set the values like this, and then so on, and then finally when we're done with this controlling, I say like from now on just connect the inputs of this like outer module into yes, and this is what I was going to ask. Like I did this and I thought it was a little bit clever, but I thought like this feels like a bit backwards. So q3k points out that you can do this with a cover statement, which tells Yosis SMTP and say, hey, find me a test bench / VCD that has this state. It's like an inverse assert, and where you can reach one is positive. That's great, because the syntax when I did this like the negative way became a bit awkward, because I had to do like one big chunk and then like a not, so it was like a double negation, so it was kind of like hard to keep it straight in my head. But I was definitely looking for something like that where I can like find me the positive case instead. So apparently you can do this. And yeah, so I mean there's some places here where it shows that I'm clearly not used to this, but I'm kind of like trying to use whatever I can. And, you know, I try to learn these concepts which I don't know about, and you know, make something out of it as quick as possible. Another thing I had like issue with is like in these this is maybe something I can get an answer for as well. In this Verilog file, like all of these outputs, they were like set to 0. So this is what I have commented out. And then when I tried to like compile this and run this, it complained that these outputs had multiple drivers, which and that also gave me like strange test results. So it wasn't until like I commented out all these zeros that things started working reasonable. I don't know if that was just like something else I messed up or something I misunderstood, but I found that it wasn't until like I got rid of like all the warnings, things actually started working correctly. But anyway, that was some test cases I set up, and I found this like initial state, and then I tried okay, so this equals 0 probably shouldn't be there for wires. No, so okay, so that's actually maybe like a flaw in the design, or what you would call it. Anyway, I used this to try create like an initial state, and then I said go from this initial state, try to find a case where like some things I was looking for was, can we find a state where this write address is outside the ring buffer, and this is where I was like, this was the second time I was closer to the solution than I thought. So the first time was actually at the end of the stream when I had things up and running. I had this situation where after sending, like I was like spamming, just sending empty packets or just sending packets in a quick succession, and I managed to get into this loop where it just would keep resetting. And I thought that this was just, you know, like I made a mistake, a bug in the setup, or you know, it's not supposed to handle packets that quickly, or like what I should have thought, and the correct way to think about this is like, oh, that's interesting, I should look into that. But since I wasn't really confident enough on this area, I just, I didn't think it was interesting. But this is actually, like, this is the vulnerability, and we'll see how very soon. So I also tried to do these things like, if we're in like a sending, like a write mode, can we get the write address to be outside the ring buffer? Or if we are in a read mode, can we get the if we're actually reading, can we get the read address to be like outside the packet size range? And I tried running this, and the code didn't look like this initially, and like it's just came up with this thing like, yeah, if you have just reset the board, reset the whole device, then you will write to address 0. And I was like, yeah, well, that's kind of obvious, but it's also kind of not interesting, because the ring buffer will be set up, and these read and write pointers will be set to something interesting. And that's where I was wrong. So there is this part in the firmware of the flag verification routine where we have an attempts counter. It's a global variable which is increased every time you make an incorrect guess. And if it is above 16, then we will run this e-break sorry, the fact that you saw got with formal is what is TOT? We'll probably get an answer to that pretty soon, but thank you. The fact that you got this with formal is super. Yeah, well, I mean, I kind of, but I also kind of didn't, because I mean, I didn't trust the output of, or like, I thought that the test case, the counterexample that the verifier gave me back, I didn't think that was interesting until like after the fact, and I realized that like, oh, I had been looking at the answer the whole time, and then I felt really silly. So let's see in what order did this happen. So, oh yeah, I should finish up this. So we would call the e-break instruction, and this is like, from now on is where we get into like RISC-V assembly land, and that's a very unexplored land. Like, the documentation is poor, the tooling is non-existent, and this caused a lot of headache, but it worked in the end. Basically, I don't know, I googled like RISC-V instruction set, I think. You can get this. Maybe I didn't actually talk about this, but like RISC-V is like an open source, like a research. It's a computer architecture, which is like a research project, like open source computer architecture, which has gained some attention in like the last couple of years. It's an interesting idea. I have no idea like at what stage it is, or like if it's going to be viable. I saw some Twitter post about some company actually like manufacturing a bunch of RISC-V processors, so I think it's like definitely something to look out for. And this is like a manual with it's the instruction set architecture is, I think this is called ISA, and I have never really read like an ISA before. It's very dry. It's all about these, like how the instructions are structured and organized and what they look like and so on. So I did not read most of this, but one interesting interesting thing to note is that, like, on the, I guess this is like a difference between like the actual like hardware view of it and like the programmer's view of it. So in this like hardware view of it, we will have some like registers, and we just name them X0 to X31, like just 32 registers. But when programming this in like RISC-V assembly, they will have other names. So here is like a mapping. So for example, the X1 is called like RA, and then these like X10 and upwards are called like A numbers, and then so they have like different names in like in hardware or in assembly. And that was something I didn't really know about. Another thing is like the difference between the actual like hardware instructions and like macros or like virtual instructions when you're doing assembly. So for example, if you want to load a 32-bit constant into a register, you can write that as a single instruction when you're writing the assembly, but that will actually be translated into two instructions, which will be actually run on the computer. It will load like one half of the, or not exactly half, but one portion of the constant in one instruction, then load the other portion of the constant in another instruction. I Google for RISC-V green card, like now or when I'm done here. So yeah, other than that, there's a lot of thing which is similar to other types of assembly. I guess if you have programmed like MIPS or something like that, which I haven't, but I guess you would find a lot of things you're familiar with. Anyway, the e-break instruction. This will essentially reset the device. And we can see that because if we run this again without the debug output and we connect to the device, and we do this, and then we should trigger the reset, and you see that it kind of reboots the processor because the main banner is printed out again, which is part of the main function. So if we do 17 attempts, it will reboot the device and like reset everything. And I noticed that if you do this, oh yeah, now I have commented out something. So what happened was that if you sent all these packets in a quick succession, you would get this thing where you just had reset, reset, reset. So I thought, like, why is it continuously resetting? There must be some kind of error. So I wanted to look at like what is the value of the program counter, like the instruction pointer, when it does, like, is it just like, is it stuck on some kind of strange address where it's in the kind of like a loop resetting or whatever. So in this varilator you can expose registers from the hardware design into the C++ code, so you can look at them like C++ variables. And I'm not sure if there was already a way to do this, but what I ended up doing was that I went into the processor specification. So first of all, I wanted to look at the I want to look at like registers, and I want to look at memory. So there is this statement, like a comment you can add to the Verilog code, which is this, like varilator public. This means that varilator will expose this register as a variable to the C++ code, and you can look at it. So I added this to the program counter register, and I think it was already in the memory module. Maybe this was already there. There was one of these statements was already there. I don't remember, but anyway, this enabled us to. I also added it for later use. I also added it to the X14 and X15 registers, but let's don't care about that for now. So in this is like the varilator code where we are like simulating the device, and we have this loop where we run a clock cycle, and then we do like accounting, like if we did a trap, we reset the device, we toggle the reset. So here is where the reset pin is actually toggle. It's toggled for 10 cycles and then switched back. And here is where we're sending like Ethernet out and so on. So we run a clock cycle, and we do like all of these. We take care of the external interfaces, and then we do it all over again. So what I did was I added this print statement where I checked the value of the program counter, and let's just add that one, and then skip these. So the only thing now that we're doing is in every cycle we are printing out the program counter. Let's skip all of these other printouts so I think this was like the first thing I did when I had this idea. So we recompile it, we run it, we connect to it, and we see here we are like, this is the value of the instruction pointer. So it seems to be working the printout, and then we can see what happens when we trigger this bug. So it resets, it runs for, no, this is not correct, this is something there's, I am probably I'm trying to show that what happened was that I got kind of like in just a loop. Let's just put this here, and then I can comment out this whole block. So we triggered a bug by sending a lot of packets. And now this is what happened. I saw that it basically entered a loop where it switched between 0, 2, and then this address. And then it hit the reset, and then back at 0, and so on. So that was interesting. Like why 0? That's reasonable because when you reset the program counter to 0 as well. And then maybe it steps forward one instruction, but then it suddenly ends up in here. And I guess that I would assume that this is like not the valid instruction, or something goes wrong and it resets again. So what happens here? And this is, yeah, this is where I used another feature of this varilator thingy. Let's just restore all my printouts. So in varilator, you can tell the program to dump a VCD file. So a VCD file is just like the state of all the signals over time, which is what you could view in this GTK wave program. So let's see if it's did any of those survive? Okay. Yeah, I'm not gonna like bother to recreate that, but basically we can just take out like a screenshot or something of this. So we would have something like this in this program, and here it would have the structure of our circuit, and then with all these different like wires and registers and stuff, and you could pick a subset of them and plot them over time. So I took out like the program counter and the memory. Yeah, so that was what I did. Like I checked like what is the and now I don't remember actually if I did it here or if I did it with these printouts, but basically I wanted to know like what's in the memory at that point, because if we look at the original firmware, so here's another issue with RISC-V, that neither IDA nor Binary Ninja like properly supports it, at least out of the box. But fortunately, Radare does. Unfortunately, I'm not very good with Radare, so that was another opportunity to shape up my Radare skills a bit. But finally, after like digging through like some Radare manuals, if we look at the code, so we are at position 0, and this is where we start by jumping to the start routine, so which is further down. So in a normal execution, we should not, like the program counter should never be at address 2, because we should jump over that. And this is actually found in the start assembly, so this corresponds to this. We jump to the start routine, which is further down here where we initialize all the registers, we set up the stack, and then we call the main function. If we would go to this here, we would see that it's actually at address 15A. So we should be jumping, like the initial routine when starting the firmware should be like, first we should execute at instruction pointer 0, and then we should jump immediately to 15A. We should never reach address 2. So why is this happening? So what I did was I either checked here, I don't remember, I used this a little bit. I like went back and forth between looking at the these wires. It's nice because you can really check absolutely everything going on in the processor. The downside is that it like takes a bit to generate. The file gets ridiculously large very fast because it has to keep all of these values, and so just like running it for a few seconds gives like a 1 GB file. And then I combined this with doing like printouts in Verilator like this. And what I found was that the value of, and this is where everything, like where I reached enlightenment. This was the magic moment. I'm just gonna see if I have like a dump of that. Well, I'm just gonna yes. So when I looked at the memory, and when I inspected the memory at this crash, I saw that the value of the first 6 bytes of the memory was this: 2, 42, 71, 33, 6B, and 21. And that looked familiar. And then I realized that it's the MAC address. So the packet had been written to memory starting at address 0. And this is when I realized that the counter example I got from the formal verification was not to be disregarded. It was actually showing me the exploit. So, or not, but at least the vulnerability. So the vulnerability is that the Ethernet, and I wanted to double check this, the Ethernet controller does not wait, like it does not care about whether the this ring buffer has been set up or not. If we check where this ring start pointer, for example, is used, here it's written to, here it's initialized to 0, here it's read from if you're reading the status, here it's used to calculate if we are overflowing or not. So actually there's nowhere in this code are we checking that this has like a sensible, or it's initialized or something before we start using it for writing data. Okay, so that's like a huge progress. That means that we have like a somewhat controlled write to the start of the memory to address 0. Also, this explains the jump, because 0242 happens to be a valid instruction, and then this 7133 is a jump to this address, which is the address we encounter afterwards. And then I guess this is not the valid instruction at this address, and then it crashes, and then it repeats this loop. So this is great news. This means that we can write almost whatever we want to the first 184 bytes of the memory, except that the Ethernet controller will only accept data. We have this, the interesting flag, interested. We will only receive data if it begins with the MAC address or the broadcast address. So the restriction we have is that q3k points out, if you added control receive ring end to 0 and the control receive state to 0 in the reset block, that would fix it. Oh yeah, okay, so this in the state we actually have like the enable receive thing. Oh yeah, and that one controls the FIFO RX flag, which is then used to write the data. Okay, so the actual bug is that we do toggle, like there is a control for whether we should start writing or not. The problem is that this is never, we don't ever reset this. So this will stay active when we reset the device. Okay, so that's the actual bug. Okay, interesting. I mean, I didn't know exactly what was wrong with the device, like what is a root cause of this was, but I could observe that it didn't care about any like controlling or some flag or something when it received, like it started receiving right away. So the problem now then is that okay, we can get it to write data to starting at 0, but the restriction is that the first 6 bytes has to be either the MAC address or all Fs. The problem is that, okay, sure, this happens to be a valid address, but this also happens to like jump away all the way to somewhere where we don't have any control. The other alternative is all Fs, which we can see down here is also not valid instructions. So the problem is that the only 2 things we can write into the memory address 0 will just crash the device. And so here I'm already like implying that our intermediate goal is, so notice now how I talked about these 2 possible intermediate steps, like reading arbitrary memory or writing arbitrary memory. We kind of went with we found some way to write arbitrary. It's not really arbitrary, it's always at memory 0, and the value is not completely arbitrary. We have this constraint, but it's, you know, write almost whatever we want to a specific location, and that's good. One other interesting thing to note is that, I mean, this memory has no concept of like write protection, or I mean, since the Ethernet controller is just writing directly to the memory cell, it will just overwrite the code. So we don't really have to care about that. But then I had an idea, like what if we could time it so that we reset the device, which will put the program counter at 0. We will start running at 0, which will then immediately, the first instruction will be an immediately jump away to what did I say, like 1.5a, and that will bring us to the start routine, which will run a few instructions, and then it will eventually end up in the main function, and here we will set up the ring buffer. So what if we could sneak in a packet in between those 2 times, like after we already executed the instruction at 0, but before we set up the ring buffer in the Ethernet controller. That would be nice, because what is next to the start instruction here, or the like reset handler, it's the interrupt handler, which starts at instruction like hex 10. This is the function that's called whenever another packet or whenever a packet is received. Like after we receive the packet, we will call the interrupt handler, which will then call the like Ethernet process thing. So that means that if we can manage to reset the device, executes this jump, then we overwrite these 184 bytes, and then a few cycles later the execution will start here and run this code that we have injected. That would be nice. So as this was like really an area where I'm not super confident, like RISC-V assembly, I took this like baby steps. So my first goal was just to like, is this feasible at all? Like, it's a pretty tight gap here. It's just like a couple of instructions between this reset and this writing to the register. It's let's see, I mean, it's from the start point. It's these instructions. What's that, like 30 something instructions, and then like a couple of instructions. What really helps us here, and I think this is really like, this is what saves the whole thing. It's like this whole print, all these calls to printf to print this out, which will add a whole lot of instructions before we actually reach this thing where we set up the registers. Like if this block was placed up here, it would be extremely difficult, or like extremely tight, to trigger this vulnerability, I think. But I just wanted to test this basic like assumption. Can I even like sneak the code in between? Like, is that even possible? So what I did was that I set up this block in the varilator. Like, because we're gonna go to this instruction, and I know what instruction is supposed to be there. This 09A0, and this is like with the other endian. So I just said, like, if the instruction pointer is at, oh sorry, not, yeah, here, okay, yeah, q3k also points out that all these prints will fill up the UART and stuff like that which like will halt the execution of the processor. And it says might have been intentional. Yes, I realized that. Like, otherwise it would be like theoretically possible, I guess, but yeah. And then over, like, when, I mean, this is all still only just locally, like over network, it would have been horrible. Anyway, I set basically up this trigger. Like, if we can get the instruction pointer to reach hex 10, and the value there is it's not what it's originally, then we have managed to trigger this bug. So I ran this, and basically I just tried different timings. I set up my Python script to first we just send 17 UDP packets with just a couple of A's, doesn't really matter. And then here I was fiddling around with like timing, and we sleep for a certain amount of time, and then we send this raw Ethernet frame, which just contains the MAC address, and I think I just padded this out with something, whatever, on the this tunnel interface, this tap interface that it's created. I just ran this a couple of times, like fiddled around with the timing. So basically, I could do like a binary search here, because if I put the value too low, then I would crash the device. If I put the value too high, waited too long, then it would just like survive the whole initialization step and set up the buffers, and then the device would be functioning as normal. So I could, like, I started trying out with 0, the device crashed, and like 1 second, and it survived, and then half a second, and like binary search down, and found that on my local device about like 0.345 second was a good stable value, which would work almost all the time. And I ran this, and I managed to trigger the print, the trigger printout. Okay, so now we now basically can write memory, and that memory will be executed. So we have pretty much arbitrary code execution on the device. Now it's just a matter of like getting the flag out of there. And this took way longer than it should have taken, because I'm actually not that familiar with like writing assembly, and especially not writing like shell code stuff. I think I maybe like started with this too late, where shell codes wasn't really like the way to go, because you actually had memory protection and stuff. But it's really nice that like all of this 90s stuff is coming back, so that I can like learn all the stuff I was too young for back then. Like when the Smashing the Stack for Fun and Profit article came out, I was like 5 years old or something. So I started like trying to write some RISC-V assembly. So first, now I had kind of like realized, or we have reached a step where we are able to inject arbitrary code into the device, and we need to get the flag out. So how do we do that in the simplest way possible? The only way we can communicate with the device is sending these packets. So we should construct a packet which will contain the flag, and we will send that packet back to us over the Ethernet. So the first attempt was just like, can I send a code which will just send back a packet with a fixed value, because that way I don't have to interact with like other parts of the memory and stuff. So I created this like assembly file first, like trying to reconstruct the situation where we will be. So we first start at address 0, and like here will be the MAC address we've overwritten, and then there is some like padding, and this means that this instruction will be at here our code execution will start. And here I made a lot of mistakes due to not understanding how like RISC-V assembly works, or just how to write assembly in general. One particular thing that bothered me was that I wanted to be able to have these like labels to reference other parts of my payloads, but when I compile this with GCC, it would just like leave them out as like zeroed, and this is due to like it's like a middle stage of the, like it's assembled but not linked, right? So in a real code, if you would link this, the linker will then like fill this out and turn these like relative addresses into like absolute relative addresses, if that makes sense. So I had to realize that, and also do like the linking part with 0 as the base to actually make it fill out the proper values. So when I had that set up, I basically had a payload where I would send this as part of the my payload, and this is an Ethernet, like a manually created Ethernet frame. So I would use like looking at the Wikipedia page for like the Ethernet frame, or even looking at the firmware, like in these structures here. Like the Ethernet had like 6 byte of MAC address, 6 byte of MAC address, the type. So I would put this payload here, and in my I modified like the VPN client script a little bit to set a fixed MAC address on my end as well, so I didn't have to change the payload. So we create a payload which should send to this MAC address from the MAC address of the device, and then just this is some ABCD repeated a couple of times. So the first step was just like, can I get the thing to send this back to me? And I mean, this took there were so many mistakes here, like for example, the register, where is it even? yeah, so here is the address of this register for the Ethernet controller. I had like missed to type 2 zeros there, I think. So, and then I was wondering like, why isn't this working? And I really was in this situation where you try one thing and it doesn't work, and then you think that idea doesn't work, but in reality it's just because you have this other mistake which ruins the whole thing. So first, and I'm still not even sure, like first I tried to read the packet directly from the memory of the CPU, and that didn't work, and I'm not sure if it like should work or so, but so I started thinking like, okay, maybe I actually need to like copy it into like real memory and then give that pointer to the Ethernet controller. So I thought like, okay, then I could just use the memcopy function, but then that wasn't working. It was still not sending anything, so I thought like, oh, maybe I need to set up the stack properly. But in reality, I just had missed two zeros here, and that's why nothing was working. But then when I actually found that mistake, I still kept these like memcopy calls. And when I compiled, so the strategy was to first just send this constant packet, and eventually I managed to do that. I sent this payload, and the way I did it was to specify, like this is the way I kind of like specify. I forced these labels to be located at certain addresses because I looked them up. If you drop the VPN client and communicate directly with the Verilator shim, what you sent didn't have to be a real Ethernet frame, but any data you wanted. Oh, I didn't even think about that. I was like, I constrained myself within the kind of like the rule, like the scenario that we had here, that this was like a device on the network, and oh, yeah, that's great. Okay, so the filtering was done. Okay, yeah, but that's good to know. So I looked in the firmware. Like my locally compiled firmware. Why is it suddenly not showing? Oh yeah. Yeah, so from this analysis I could pick out like the location of like the memcopy function and the other parts, and then I would put them here in this and force these labels to be located in these different locations. My first idea was actually to skip the Ethernet part and just for test purposes just try to print it on the UART. Of course that wouldn't be like the real exploit, but as a first step I thought like it's easier to just print it on the standard out than trying to do the network stuff. But I failed with this. Maybe it was because I hadn't set up the stack, or I don't know. This was just in this middle of this mess of mistakes I did here. But anyway, one crucial part of this was that, or like, I mean, I don't really know where the flag is going to be on the remote machine, but for starters, I started with the local thing, and since I have the firmware, the actual firmware running on my machine, I could go to the process flag function and then check no, sorry, actually the check flag function of this firmware, and we would see that it would here load this here address, which is the pointer to the flag, which is this. So my idea was then to first I tried this static constant thing, and eventually after this mess of errors I actually managed to send this back. So then the strategy was like, okay, I still keep this like template, but then I should overwrite the payload with the contents of the flag. So what I did was first I copied the this like packet template into, I used memcopy to copy it into some area of the RAM, which like I looked at this this defines here in the no, actually it was in this interconnect thing. I think it was also like a memory map. Yeah, no, actually, I thought that, okay, so yeah, I figured out that somewhere about here I should probably be able to write the yeah, that was I just chose some address which should be in the like the regular RAM that felt safe. So I used memcopy to copy the template over, and then I took the location of the flag pointer, dereferenced it, and copied that into almost like the same location, but of course offset. So I copied it into here. And when I ran that locally, that worked just fine. I can actually show. I'm just gonna remove that part and that part, because this is stuff I had to the problem is then that this didn't work live, and I'll come to that. But the way I did it was that I first compiled it with GCC, and then, as I said, I had to link it as well. Had to be in the right directory, which then produces this binary file, and then I just opened it in hex editor to check where the actual code is, and comparing it like in the actual the file offset, and it starts here. So the offset is like, let's see, can I zoom in? Yeah, okay, it's just using a hex editor finding where the code starts. I compared it with the output of Radare. So it should start with 1711, and this is here, which is hex 64, and that seems right here as well. So then in my exploit script, I would just read this file and then jump to that offset and read a couple of bytes, and I would append that to this Ethernet frame that we're going to send. But we need to make sure that, so first we put in the correct MAC address, but then we need to pad this out, because as we said in the startup here, we're gonna overwrite 6 bytes here, but then we need to overwrite another 10 bytes to get here. So just pad it out, and then the actual code. Running this, let's see if this works. So we run it, and then this was like my super messy setup. So I have the VPN client connecting to the device. Cool. And then I just ran TCP dump on this device. And then I ran the exploit. And boom, you get the flag back on the Ethernet device here in TCP dump. Okay, great. I thought then I'll just run this on the target, and we're done. That's what I thought. So replacing this with the real target, running TCP dump. Let's check that the delay is like reasonable, and then run it. But we don't get a flag back. We just get other parts of memory back. So it seems that the flag pointer is not at this location in the live target. So that was a bit disappointing. And I thought that I would be smart, like trying to identify like where is this in my local binary, and then try to like calculate some offset and trying to be smart about it. But I ended up just simply trying a bunch of different offsets. Like I didn't even use, like, all of this is just bogus. I just like loaded this constant, which I think is where the banner is on my local firmware, and then just typed different values here. I just searched back and forward a couple of times. So let's see if I can manage to do the same thing live. So let's reconnect, so we properly reset the device, set up TCP dump, run the payload, and that did not work. Oh, I didn't save the file. That helps. If you're changing the file, you should save it, and then run the TCP dump, and so this loop of like changing a little bit, like disconnecting, reconnecting, fiddling with values. I repeated this a lot of times, and yeah, now for some reason it doesn't work. So I was just fiddling these values back and forth, and finally I hit the right offset and managed to dump the flag. Yeah, so that's pretty much it, I think. Is there anyone still listening? Any like questions, comments? I thought it was a really interesting challenge. I learned a lot about like Verilog and hardware, and like how to like this simulation and formal verification thing. It was exciting, and it's, I think it was just very a good example of these like really big complicated challenges where when I start I feel like this is never gonna work, like I have no idea how to do this, but then as you progress, oh, Now I see why this is not working. It says command not found. I'm really stupid. I'm just now gonna actually try to run this again to see if we actually can get the flag out. Would be a nice conclusion to this. Yes, it did work. I just I did the same mistake when I was sitting up in the middle of the night and doing the final list. So for some reason I messed up my my paths a little bit. So I have to run this source this file to set up the path. And I know that when done correctly, the linker will output this warning. But also if you run it and you haven't set up the path, it will output this. And if you're sloppy, this and this are the same things, which it's obviously not. Anyway, so now when I adjusted this and actually compiled a new version of this and ran it, you see here we have dumped a part of the memory. I missed the 2 first character here, but I guessed that it should set flag. And then we have this part. And the flag was, have you embraced formal verification yet? Yes, I have embraced formal verification. So yeah, very nice challenge. Thank you, q3k, and a nice little hype train we managed to get around this. It really helps your viewer count to get like signal boosted by live overflow. So thanks for that. Yeah, I will be going to DEF CON next week. So if anybody want to meet up, like I will be quite busy. I'm going there for a HackerOne event, but like I'm available like during the day. So if anyone want to have like lunch or just meet up and talk or something, it's just like message me or something. That would be great. And yeah, as I said, really enjoyed the challenge. Hope I will do some other kind of like these like blind solves or walkthroughs or whatever. Like if you have any like suggestions or something that you would like to see, or you know, whatever, just like comment or message me or something, and we'll set something up. So with that, I'm going to stop this stream now. So have a nice evening or whatever it is in your current time zone, and I'll see you sometime. Yeah, we should. I'll send you a message live overflow, and yeah, have a nice day, evening, morning, whatever. Goodbye.